Okay, so we're going to look at how to find the derivative of exponential functions. So remember, that's a function like, say, 2 to the x, or 4 to the x, or even e to the x. Okay, so where your variable x is in the exponent. So our derivative rule, in the interest of saving time, I'm going to hop right to the rules. Of any base to x is going to be equal to itself. So the rate of change of a exponential function is proportional to its actual function value. We can talk more about that in class, but this is interesting. The derivative of an exponential is itself. So the differentiation rule here is pretty darn easy. Whatever the function is, that's also the derivative. The only caveat here is we have to do times the natural log of the base. That's the concept of proportionality here. So then, of course, we do have to consider the chain rule. What if I have a base a and the exponent is not just x but a function of x? We'll call it u. That implies that it's some function like, x squared plus 3 or something like that, or sine of x. So if we write this rule for chain rule, it's still going to be itself times u prime. That's the chain rule part. That's the derivative of the inside. And then times the natural log of the base. Okay, so natural log of a. So those are our rules. So let's try it. We're skipping these because I'm doing these in a different order. So this section of notes is not, we're not going in order. Darn it, I didn't charge the pencil. So we're back, it's charged. You're skipping ahead a couple sections. We're going to go backwards through this. So let's apply it. The derivative is going to be equal to itself. So that's a pretty easy start. The inner function here is x squared, so we do have to apply chain rule. So times the derivative of the inner, which is 2x, and then times the natural log of the base. So there's our answer. We could write it in a better order. 2 is just a number. ln of 4 is just a number, so I kind of like to write those first. Then times x, and then I usually write my exponential last. Let's try a product rule one. So here's my f and here's my g. So the first one's power rule because the x is in the base. The second one's the exponential rule because the x is in the exponent. So it's not power rule. We can kind of get mixed up there on that second one. So the derivative of the first is 2x times, I recopy the second, 2 to the 2x, plus recopy the first, times the derivative of the second. So when I do the derivative of this, it's itself because it's an exponential, so it always starts off easy. But then I got to apply chain rule, so times the derivative of the inside function, which is 2x. So that's going to be 2. And then times the natural log of the base. A lot of 2's in this one. So what I'm going to do is I notice two terms. I'm going to write each term in a better order. So I already like to order the first term because I like number, then x's, and then exponentials. So here I'm going to bring this 2 and this times ln of 2 all to the front, times x squared, and then finally times my exponential. Now I'm looking for a common factor here. So it looks like I've got the 2 in common, so I'm going to factor that out. Looks like we have an x in common, so I'm going to factor that out. And it looks like the exponential is also in common. So that's my common factor. So now when I go divide it out, it all divides out of that first term and we just have 1. And then plus the 2 divides out. I've got an ln of 2 left, and I also have an x left. These, you can pause the video and do them here or come back to them for another time for practice. There's your answers if you want to write those down. Moving along, same here, some more product rule, a quotient rule down here on the right. You can pause the video and write those down if you like, do them, whatever. So we're going to do a quotient rule 1 here. I do the derivative of the numerator. It's an exponential because the x is in the exponent. It's not power rule. So the derivative of an exponential is itself. But then I have to apply chain rule, so times 5 because that's the derivative of the inside function, then times the natural log of the base. Minus, oh, whoops, that was just the derivative of the top, times the x. Now I go minus, recopy the top, and then times the derivative of the bottom, all over the bottom squared. So again, I see here that I have two terms. So first I'm going to put them in a better order. I like the 5 and the ln 3 as a number to come out front, times x, and then times the exponential, 3 to the 5x minus 3 to the 5x, all over x squared. So I could factor out a 3 to the 5x, yes. So it'll be 5 natural log of 3x minus 1, all over x squared. All right, here's one where we can do an application. For what values of x would the graph of blah, blah, blah have a normal line whose slope is 2? A normal line whose slope is 2. Show your work and explain your reasoning. So here's the answer. I'm going to just help you set it up, and then you can pause it and go for yourself. So since the normal line has a slope of 2, that's going to occur at the same x value where the tangent line has a slope of negative 1/2. So I'm going to find the derivative of p. So this is an exponential. The derivative is itself times the chain rule, the derivative of the inside, times the natural log of the base. I'm going to set my derivative equal to negative 1/2. And this is a calculator thing. So I'm going to put this in y1, this in y2, and find any x values where they intersect. This should be your answer. So you can pause and finish that off and see if you can do that and get that answer. All right, moving along. How do we do logarithmic functions? So the rule for a logarithmic function of log any base a of x is going to be 1 over x. So it's like what's inside here, right? 1 over x times 1 over the natural log of a. And of course, we can write that more succinctly as 1 over x times the natural log of a. Of course, there's always chain rule we have to consider. So log base a of some function u, so that implies that, again, I have a whole function in there. It's going to be 1 over u times 1 over u times the derivative of the inside, u prime, so there's your chain rule part, then times 1 over the natural log of a. So if we write that more succinctly, you can think of that as over 1. It's going to be u prime over u times the natural log of a. Okay, so we're going to skip these again because we're going out of order. Let's try to apply it here. So if I do my derivative, this looks like a chain rule because I've got a whole function in there for of x, not just simply an x. So it's going to be u prime over u. So I like to start with the denominator. I recopy the u. It's going to be this stuff in here. That's my u times the natural log of the base, which was 2. Then what goes up top is u prime, the derivative of the inside of the log, which is 4. So then those 4's can cancel, and we have 1 over x times the natural log of 2. This kind of bugs people out that we don't have our log base 2 in here anymore, but that's just the way it goes. Here's one you can try on your own. Here's another one you can try on your own. You can pause and write down those answers. We're going to do another one here together. So again, I've got the derivative of a log, and it's a log function because the stuff inside the log has the x in it. So this is like my u. That's my inner stuff. So I'm going to go, I do it the denominator first. It's always the u part, so I recopy it, cosine of 3x times the natural log of the base, which is 5. And on top, I get u prime. So the derivative of cosine is negative sine. I recopy the inside stuff. But this is chain rule again, so it's like a chain rule inside of a chain rule. A double chain. 2 chain rules. It's crazy. So that's where that times 3 comes from. It's the derivative of the 3x. So now if I want to simplify here, I can think of this as this. I'm going to call it negative 3 over 1 times, you don't have to write all this out, but I like to show it the first couple times so we can see how I organize it kind of in my brain. So I could really call that negative 3 times the tangent of 3x times 1 over the natural log of 5. So it becomes negative 3 tangent of 3x all over the natural log of 5. And there's a couple different ways that you can write that, but I kind of like this way. keeping in mind that the natural log of 5, these are just numbers when there's no x in them. Okay? So here's another one you can try on your own. A couple more you can try on your own. We're going to do this one together. Don't write this down. You're going to put your pencils down and relax for a second. There's a better way to do this. I want you to watch this painful way so that you can never forget to not do it this way. Okay, you don't want to do this. We're going to do it this way, then I'm going to show you the better way to do it. All right, so I do the bottom first. I recopy my u. This is my u, all this stuff inside the log. I hope you're enjoying your vacation here. Watch me do all the work. So it's u times the natural log of the base. Then I have the numerator, the u prime. So that is going to be a quotient rule there. So this is where it gets annoying, and we can avoid this part. So I do quotient rule on this. I get 3. I'm just going to kind of blast through it because we're not going to do it this way. The derivative of the top times the bottom, minus the top, derivative of the bottom, all over the bottom squared. And then how do I simplify this thing? Up top, I've got my 3x minus 3 minus 3x all over x minus 1 squared times, it's going to be x minus 1 over 3x natural log of 3. So then I simplify a little more. These go away. I've got negative 3 over x minus 1 times 3x natural log of 3. So then these 3's cancel. I got negative 1 over x times x minus 1 times the natural log of 3. All right, so this way kind of sucked because we had to do quotient rule up here, and we ended up getting a fraction, excuse me, inside a fraction. To arrive at our answer, we have to do a lot of simplification. What we're going to remember instead is before we do these derivatives for log functions, if we can apply a property of logs, we want to do that. So before I do, notice I'm not doing the derivative. It doesn't say q prime. Log base 3 of 3x minus log, well, I thought I wanted to make a circle, minus log base 3 of x minus 1. I can separate them out. This minus sign allows me to do the derivatives each independently. So here I can say this derivative is going to be, the u is 3x, right? So 3x times the natural log of 3. And the derivative of 3x is just 3. These will cancel. Minus, over here, I've got x minus 1 times the natural log of 3 again. And the derivative of x minus 1 is just 1. So then I've got 1 over x ln of 3 minus 1 over x minus 1 of ln of 3. And if I wanted to add these together, I could get a common denominator. I'd probably accept this, but I want to do the common denominator to show you that it's the same thing as that. So my common denominator here is going to be x times x minus 1 times the natural log of 3. This numerator needs to get multiplied by x minus 1. This one needs to get multiplied by x. X minus x cancels, and we end up getting the same answer, negative 1 over that stuff, which is what we had before. So always, always, always apply your properties. Even here, I'm not going to do this one for you, but I'm going to show you the setup before we do the derivative. This is still just k of x. So properties of logs say that if I have, well, let's think of this as to the 1/2. I can bring that down to 1/2. It's not power rule. I'm not doing a derivative. People get confused because we're bringing an exponent down. That's a property of logs. Now from here, when I do my derivative, this is a constant 1/2 times that. So I can do 1/2 times and do my whole log derivative on this thing. Simplify it to this. See if you can do that. Here, the properties do not apply. I cannot pull this squared down because it's not this whole function squared. It's just the x squared, which is inside the sine squared. So, which is inside the sine. So you can't bring that 2 down here. You just got to go after it and see if you can get the answer. All right. So for this guy, we're not going to do this one. This is another calculator one. You can try to work this one out on your own. I was getting answers of x equals negative 0.842 and 0.342. So you want to see if you can get that.